Hello everyone. Welcome back to the channel where we dive deep into the cosmos and uncover the mysteries of the universe. Today, we're tackling a mind-boggling question. How the heck do you measure an entire universe? Grab your telescopes and let's zoom into the details. For objects close at hand, it's straightforward. We use a known length of another object as a reference to measure the distance. But what about something that's beyond our reach? We could walk to it, counting our steps to gauge the distance. Consider the moon farther than we can imagine. We send a beam of light towards it, reflecting off mirrors left by Apollo astronauts, and measure the time it takes for the light to return. This allows us to calculate the distance using the speed of light. Now, let's tackle a bigger challenge, measuring the size of the universe. On a remarkable night, October 5, 1923, Edwin Hubble pointed a massive 100-inch telescope at a fuzzy patch in the sky and captured an image that would change our understanding of the cosmos. Studying this image, and others like it, he observed a star that brightened and dimmed over time, a Cepheid variable star. Astronomers knew these stars' brightness and pulsation rate could reveal their distance. Astonishingly, Hubble's calculations showed this star was 1 million light-years away, far beyond the Milky Way. This meant only one thing: the star wasn't part of our galaxy. It belonged to another, proving the existence of galaxies beyond our own and dramatically expanding the scale of the known universe. How big is the universe then? This video explores the cosmic tools developed since the era of the ancient Greeks, tools that have helped us measure the universe from our local neighborhood to its outermost edges. Join me as we unfold the tape measure across the cosmos. The early sky watchers, those ancient astronomers, gazed up at the moon, planets, and stars, fully aware of their staggering distances from Earth. Even without modern tools, the brilliant minds of ancient Greece unlocked a fundamental technique for gauging these distances through a simple yet profound method: parallax. Imagine looking out the window of a speeding car. Nearby trees whip by swiftly, while distant mountains barely seem to move. And the stars? They're so far away they appear completely still. This difference in apparent motion is the essence of parallax. Now, try this. Focus on an object nearby, then alternately close one eye and then the other. Notice how the object seems to jump against its background. That's parallax in action, and it's probably something many of you are experimenting with right now. The principle is straightforward. The closer an object is, the more it appears to move against the distant background when viewed from different positions. Astronomers applied this same concept on a cosmic scale, using Earth itself as the moving viewpoint. Observing a star from different points in Earth's orbit can reveal its distance, akin to using two vastly separated eyes. This method dates back to the 2nd century BC, when the Greek astronomer Hipparchus first employed parallax to estimate the distance to the moon. He meticulously analyzed observations of a solar eclipse from two distinct locations, one witnessing a total eclipse, the other seeing the sun nearly fully obscured. Join me as we climb the cosmic distance ladder, leveraging ancient wisdom and modern science to pinpoint our place among the stars. Imagine the scene. Hipparchus, back in ancient times, knew the distance between two observation points, his two eyes, so to speak. With this data and the angle at which the moon appeared to shift, he applied some straightforward geometry to calculate the moon's distance with remarkable accuracy. Fast forward to 1672, when Giovanni Cassini harnessed the same ingenious method to pinpoint Mars' distance. It's truly astonishing how close Hipparchus and Cassini's estimates were to the measurements we accept today, all achieved without the benefit of our modern technological wizardry. Parallax isn't just for celestial bodies within our solar system, it also extends to the stars. Astronomers utilize Earth's different orbital positions throughout the year as these two eyes to observe the subtle shifts in a star's position against the backdrop of more distant stars. With a bit of math, these shifts reveal the distances of these stars. Building on this, a satellite named after Hipparchus has used ultra-precise angular measurements to map out the distances to an astounding 2.5 million stars. Yet, there's a limit to how far parallax can take us. Beyond a certain point, we need to add new methods to our cosmic distance measuring toolkit. By the 1920s, astronomers had pieced together a fairly detailed map of our galaxy. It wasn't perfect, but the spiral arms were delineated, and the major celestial landmarks were positioned. They had a ballpark figure of the galaxy's vastness, so immense that we shifted from measuring in mere distance to considering the time it would take for light to traverse such spans. And just as this expansive cosmic portrait was emerging, subtle clues hinted that there might be even more to the universe than we had ever imagined. In the 19th century, the astronomical community was buzzing about enigmatic fuzzy objects in the sky, dubbed spiral nebulae. Some argued these were merely gas clouds within our own Milky Way. Yet, a bold new theory suggested they were island universes' entire galaxies beyond our own. The debate was fierce. Could these actually be other galaxies? Enter Edwin Hubble, determined to resolve this cosmic question. On the night of October 5, 1923, Hubble pointed a colossal 100-inch telescope at one such object, then known as the Andromeda Nebula, hunting for a specific type of star known to astronomers as Cepheid variables. As Hubble examined the photographs over several nights, he spotted a speck that seemed to pulse, growing brighter, then dimmer. This was the breakthrough he needed. Cepheid variables, thanks to their distinct brightness and pulsation patterns, serve as cosmic yardsticks. Astronomers had learned from Henrietta Leavitt a decade earlier how to use these patterns to measure stellar distances. A Cepheid that pulses over 30 days, for instance, shines with the staggering luminosity of 10,000 suns. Hubble's meticulous calculations revealed that this pulsing star was about 1 million light-years away, far beyond the outermost reaches of the Milky Way. This discovery was astounding. It implied the star wasn't part of our galaxy at all, but belonged to another, effectively proving the existence of galaxies beyond our own. In a single moment, Hubble didn't just widen our view of the universe, he multiplied it, leading to a profound question that echoes in science to this day: just how vast is the universe? In the cosmic dance of the stars, Cepheid variables are the metronomes. The speed of their pulsation reveals their intrinsic luminosity. A Cepheid pulsing once every day is relatively dim, merely a few hundred times brighter than our Sun. Conversely, one that takes a month to complete a cycle can be as brilliant as 10,000 suns. Understanding a Cepheid's true brightness allows astronomers to gauge its distance based on how dim it appears from Earth. These stars are known as standard candles because their known luminosity lights the way across cosmic distances. However, when Edwin Hubble calculated the distance of a pulsing Cepheid star within the so-called Andromeda Nebula, his results were staggering. The star was about 1 million light-years away, far beyond the Milky Way. This discovery was revolutionary. It confirmed that the star, and therefore the nebula it resided in, was not part of our galaxy, but a splitting starlight into its spectral colors, much like a rainbow. This spectrum acts like a barcode unique for each star, encoded with lines that indicate the presence of specific elements. However, astronomers noticed something peculiar. These spectral lines sometimes didn't appear at the expected wavelengths. Occasionally, they were shifted towards the blue end of the spectrum, indicating yet more hidden complexities in our universe. In the cosmic theater of galaxies, a fascinating phenomenon known as the Doppler effect plays a pivotal role. This effect occurs when a source of waves, whether sound or light, is moving relative to an observer. The result? A shift in the frequency of the waves based on the direction of movement. In 1912, an astronomer named Vesto Slipher wielded the tool of spectroscopy to decode the mysteries of what were once thought to be mere spiral nebulae, but were later understood to be entire galaxies. What Slipher found was groundbreaking. The spectral lines of these galaxies were predominantly shifted towards red, a phenomenon known as redshifts, This indicated that these galaxies were not just moving, they were racing away from us at staggering speeds, hundreds of kilometers per second. Then, in 1929, Edwin Hubble pieced together a discovery that would redefine our understanding of the cosmos. The farther away a galaxy was, the faster it appeared to be moving away. This observation led to a revolutionary conclusion: the universe itself was expanding. This realization transformed the static picture of the universe that astronomers had long sought into a dynamic movie. Yet, this led to new questions. How quickly is the universe expanding? What does this mean for its future? To delve deeper into these mysteries, astronomers turned their gaze to supernovae. These colossal explosions mark the violent deaths of massive stars, briefly outshining entire galaxies. By observing these brilliant, fleeting events, astronomers could add yet another layer to our cosmic distance ladder, pushing the boundaries of space exploration and our understanding of the universe's ultimate fate. Type Ia supernovae are like cosmic beacons, all shining with a similar peak brightness, making them perfect cosmic yardsticks, much like Cepheid stars. But there's a catch: these supernovae are extraordinarily bright, allowing us to spot them across the vast expanses of the visible universe. This capability gives us the power to take a significant leap forward on our cosmic distance ladder. By the 1990s, astronomers had harnessed this ladder to sketch a detailed portrait of an immense universe, one that seemed to stretch endlessly, expanding into infinity. Common wisdom held that this expansion couldn't possibly continue indefinitely. Surely the cosmic pull of gravity would eventually slow things down, right? Yet, when astronomers observed the light from the most distant supernovae they could detect, they stumbled upon a startling revelation. The universe's expansion wasn't just continuing, it was accelerating. What mysterious force was driving the universe apart, overpowering gravity? How had this unseen force sculpted the cosmos over the millennia? Once more, reaching the top of our cosmic distance ladder not only posed new, mind-bending questions, but also opened vast new fields of scientific inquiry. Now, more than 2 millennia after Hipparchus first gauged the distance to the moon, our perception of the universe has transformed dramatically from the ancient Greek model to the stunning vista of the Hubble Deep Field. We've discovered that our universe houses more than just one galaxy, that the boundary of the observable universe extends billions of light years away, and that our universe is an ever-expanding frontier, filled with mysteries waiting to be unraveled. Yet, the universe isn't just a static photograph. It's a dynamic movie, unfolding across the expanse of time. Most crucially, our journey through space has taught us that even the simplest questions, like how far away is that, can spark a cascade of further inquiries, fundamentally shifting our perspective of the cosmos. Each answer we uncover on this celestial voyage not only expands our knowledge, but also reshapes the way we understand our place within the universe. The universe is vast beyond comprehension, stretching over billions of light years. To start, let's understand the basic unit of measurement in space, the light year, which is the distance light travels in 1 year. This is about 5.88 trillion miles or 9.46 trillion kilometers. Astronomers use this measure to convey the staggering distances between celestial objects. Astronomers use a variety of tools to measure the universe. One key instrument is the telescope, which comes in various forms like optical, radio, and space telescopes. Each type has its unique role in capturing different wavelengths of light, helping us observe galaxies, stars, and other cosmic phenomena. The light from a galaxy has redshifted. Astronomers can deduce its speed and distance from Earth thanks to the expanding universe. The universe is not just a random scattering of stars and galaxies. It's structured in a vast web of galaxy clusters and dark matter. Recent surveys and missions, like the Sloan Digital Sky Survey and the Euclid spacecraft, aim to map this cosmic web in unprecedented detail, helping us understand the universe's expansion and evolution. Gravitational lensing is a phenomenon that allows astronomers to measure the mass of galaxy clusters and the distribution of dark matter. When a massive object like a galaxy cluster bends the light of more distant galaxies, it creates a lensing effect. By analyzing these light distortions, scientists can infer the mass and structure of the lensing object, offering a unique way to map unseen aspects of the universe. The CMB is the afterglow of the Big Bang, preserved as microwave radiation that fills the universe. By studying the tiny temperature fluctuations in the CMB, astronomers can learn about the early universe's composition, shape, and fate. This cosmic relic is crucial for understanding how the universe has evolved over the past 13.8 billion years. Type Ia supernovae serve as standard candles for measuring cosmic distances. These stellar explosions are highly uniform in brightness, making them perfect for calculating distances to far-off galaxies. By observing the apparent brightness of a supernova, astronomers can determine its distance from Earth, crucial for mapping the universe's expansion rate. The expansion rate of the universe, known as the Hubble constant, is key to understanding how the universe has grown over time. By measuring the distances and redshifts of distant galaxies, astronomers can refine estimates of this rate. Discrepancies in measurements from different methods present intriguing challenges and fuel ongoing debates in cosmology. Emerging technologies and missions promise to revolutionize our understanding of the universe. Projects like the James Webb Space Telescope and the Vera Rubin Observatory are set to provide deeper, more detailed views of the cosmos. These tools will help us measure the universe with unprecedented accuracy, bringing new insights into its age, expansion, and ultimate fate. Dark energy, a mysterious force driving the accelerated expansion of the universe, remains one of cosmology's greatest puzzles. By studying how dark energy influences the growth and shape of the universe, astronomers can use it as a tool for measuring cosmic scales and understanding the underlying physics of our universe. Neutrinos, almost massless particles that rarely interact with matter, also play a role in cosmic measurements. By detecting neutrinos from supernovae in the Sun, scientists can gain insights into processes occurring at the core of these cosmic giants, helping to map out the energy production in the universe and potentially revealing new physics. Dark matter, while invisible, affects the structure and evolution of the universe. By studying the gravitational effects of dark matter on visible matter, like galaxies and gas clouds, astronomers can map out where dark matter is and how it contributes to the overall dynamics of the universe. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.